Thank you very much, Amy, for introducing me. And thank you, everyone, for attending this talk. And I'm very happy to have the chance of giving this seminar today in digital features. And good afternoon. That's the reason I'm also writing my Gmail address, not KTH, since this month is my last month here as postdoc. And soon I'm starting my new position. And today I will try to outline the foundations of the user-centric self-healing massive MIMO based on our recently published textbook on that, and also some of the last works we are conducting here in AI for Green project for the cloud-based implementation as a case study. So now you see our recently published book last year, and it's also you can find the free ebook version in the GitHub folder of Professor Emil Bjørnsen, and also the codes, free codes accompany the book for all the simulation figures. So during my first postdoc, I had the chance of collaborating with the pioneering names in massive MIMO, and to be a part of this book with Professor Emil Bjørnsen and Professor Luca Sanguinetti during my postdoc time in Linköping University. And we have covered the basic physical layer foundations of user-centric self-healing massive MIMO, which is a post-cellular infrastructure that aims to solve the problems with the traditional current cellular networks for the future generation mobile communications. And here is the outline of my presentation. First, I will start with the motivation for self-healing networks, why we focus on this idea, and then I will just describe the system model for the user-centric self-healing massive MIMO, benefiting from the notations, figures in our book, and focus on the three parts, mainly physical layer parts, channel estimation with uplink pilot transmission, uplink data communications, and downlink data communications. Then in the next stage, during my current postdoc period, I'm working in AI for Green project with Çiçek Çavdar, and we will look at the end-to-end resource allocation aspects, end-to-end power consumption, energy consumption aspects of the self-healing massive MIMO on top of one of the promising network architectures, virtualized cloud or centralized RAN architecture, and I will conclude my presentation later. Let's start with the motivation and introduction for self-healing networks, but we first start with the cellular networks, the current traditional networks, and how they appeared. Firstly, they designed for the mobile telephony, and the total network area is divided into cells, and in each cell, in the center of each cell, of course, this is just for visualization purpose. The structure can be different. Sometimes hexagonal structure is used for visualization purposes, but here we are using square cells, and there is an access point in the center, and this access point is responsible for serving the user equipments that has the best connection to it. Here you can think of in terms of distance, but in reality, of course, it is in terms of channel gain, pet loss, and plus shadowing. So here you see the wireless backhaul transmission is possible for some coordination between access points. And then there is a core network. All these access points are connected to core network. And in the basically, each access point is individually responsible for the user equipment. So this structure is inherently scalable, because when there is a new demands in some area needed, new access points can be installed, deployed, and the users can benefit from that. And it will not affect the computational complexity or signal processing complexity of the other access points. And it is also adjustable according to the traffic density. Then we can densify the structured network according to the user demands, traffic density, and we can control the interference one user creates on the other users due to transmission from responsible access points, or in the uplink due to messing of the other user signal by the power allocation, by cutting the power of some users, or fractional spectrum reuse, because after some period of time, we can again use the same frequencies due to pet loss, large pet loss, degradation. There will be no critical interference when we use the frequencies. This is the basic outline for the cellular networks. But when we look at the new requests, new demands of the current mobile communication systems, we can see that from this Ericson's graph, not voice, but the data dominates the system user needs. And we can see the increase in voice only 1% per year, but data is much greater than that. And also for the voice, there is a service requirement is not more than 100 kilobits per second because it doesn't bring any benefits, any new benefits. Just 100 kilobits is enough. But when it comes to data, more data rate is always preferable. And also the requirement is much more compared to the voice service requirements. So traditionally, these large data rate variations in cellular networks was not a problem for the voice-oriented communications. And you can see a graph here, nice graph here, like it's a two-dimensional area and it shows the data rate. When there are 4 cells, 4 access points with a single antenna in the center of each cell, and shadowing is neglected here, so just these pet losses are affected by the distance. And you see the data rate variations when a random user dropped in the area, in this area. And there are some peak data rate regions in these center regions, but also there are large data rate variations, and with pet loss, there is a sharp decay. But for the voice, it was not problematic. But nowadays, the main goal of the next generation mobile communications, actually, rather than increasing the peak data rate, because now the important thing is that also give uniformly good service, so uninterrupted data service, because this also affecting the other best users, and we should guarantee this almost everywhere in the network area. Now we are looking at some solutions. The densification of the network, ultra dense networks, is one promising solution, but again the same behavior appears. Of course, here you deploy lots of access, large number of access points, 64 here, 8 by 8, you can see, still single antenna access points. But again, since the user is served by the closest best channel access point, still there is a large data rate variations. Still there are some problems here, and interference is again still problematic. The other solution, and now in the 5G, currently available in the 5G standards, is the cellular massive MIMO, multiple input, multiple output. And it is based on the seminal paper of Marzetta from 2010. And in just 10 years, it became now commercially available in 5G standards. And this success is coming from actually simple linear processing schemes and nice theoretical formulas, and also beamforming, great beamforming and multiplexing gain, coming with the lots of large number of antennas greater than at least 64 at each access point. Then we can enlarge the regions of these peak data rates actually greatly. When we go from the shift from the left figure to the right figure, now each access point is equipped with 64 antennas instead of 1 antenna, and we can see the SNR, signal to noise ratio improvement everywhere. But still there are some regions for the unfortunate users, and this is not good. So still there is a problem with the large data rate variations. The question is, can we do better with another one? And the aim is actually, next goal is this, actually obtaining the figure in the right, uniformly good data rate everywhere. Like also solving this the low data rate issues in the cell edges. But which problems should be addressed? First of all, we should reduce the interference among the users and also this signal to noise ratio variations. But how can we do that? That's the reason how cell-free massive MIMO idea appeared in the first literature. And it's based on this paper, 2015. Actually, it's a clean slate look to the joint transmission techniques. Before this paper, there were also some joint transmission like COMP papers and some attempts in 4G, but there were some unsuccessful trials and some failures due to high signaling requirements between the access points and also due to channel state information sharing. But now from cellular massive MIMO, we have some tools. We have simple linear processing schemes, and how can we use these ones? And how can we benefit from massive MIMO deep theoretical knowledge under Massive MIMO. That's the clean slate look to the cell-free structures, and it's the cell-free Massive MIMO now. Now there are low-cost access points, as you can see in this figure. You can see it like the single antenna access points, not like 64 antenna access points. But why we are using Massive MIMO? The Massive comes from the distributed, located lots of access points. Now in the area, still large number of antennas serving jointly all the users. So here, for example, this user, yellow user equipment is the canonical form, the original form of the cell-free Massive MIMO served by all the access points. Of course, this is not scalable, and we will come to that point. But in that way, we can both benefit from macro diversity and also handle the interference, like by joint transmission facilities and like using all the channel state information of all users. But also from our book, we can see the definition of this cell-free Massive MIMO, either considering the original form or the scalable version that I will come later. But we consider a network with L access points, and these access points jointly serving all the users. But this access point has a fairly small number of antennas, unlike cellular Massive MIMO. But still, there are the number of user equipments that are simultaneously served is much less than the number of available access points and also the number of available antennas. So it's the Massive MIMO structure. And the access points are interconnected via frontal. These dashed lines denote the frontal connections to one or multiple central processing units. And these central processing units are now responsible for the coordination of these access points and also for some processing according to the implementation of cell-free Massive MIMO. But the thing is that this clean slate look actually benefits from both physical layer formulas, physical layer nice theoretical tools from cellular Massive MIMO, and also increased macro diversity from the ultra-dense network. And also in line with the COMP technology, it benefits from this joint transmission and reception facilities. So we can think of cell-free Massive MIMO as a combined technology that can benefit from each these three promising technologies. Now, how can we do this cell-free Massive MIMO scalable? That's the question, because if each access point serves all the access points serve each user, then it is of course not scalable system. And the idea used in the 4G is the network-centric clustering. When you see on the left figure, now you just define cells, but also clusters, and the colored regions denotes the clusters. And in each cluster, there are multiple access points, and these access points cooperate, jointly serve the users in that cluster. This is, of course, a scalable solution, but still there is a cluster edge user problems now. Maybe here, if the user is in the center of the cluster, no problem. But if the user is next to the edge of the cluster, still interference is a problem. And it is not in line with the cell-free philosophy that we aim uniformly great service everywhere. So now user-centric clustering, the idea of user-centric clustering appears. Now we look at the problem from the user perspective. That's the reason we call it user-centric, because each user equipment is served by a limited number of access points, but the promising ones, like best ones, hopefully best ones, but a limited number of access points. So now the user is at the center when we think of visually. That's the cell-free philosophy. And now we continue, as we covered in our book, with the scalable user-centric cell-free Massive MIMO. And due to the inherent nature of this structure, the clusters are potentially overlapping, because now, according to the user demands, maybe one access point will serve user one, but maybe the user two with the other access points. So these colored shaded regions denote the user-centric clusters. But since the number of access points serving each user is limited, we have a scalable system. And also, we can claim that, we can prove this statement, when the total number of users goes to infinity in a considered network area, if the number of users that are served by each access point is finite, then we can claim that signal processing and frontal signaling flow from the access point to the central processing units is scalable. So we can design a scalable system in terms of signal processing and frontal signaling flow. And also here the signal central processing units are shown as like a physical unity, but we can also imagine them as a logical entity in the network. Maybe it can, they are just for coordinating the processing and the access points, orchestration of the access points operations. But it can be maybe one master access point, not like a very big cloud structure like a central processing unit. But here is a visual representation. We present them in the like as a separate entity, but it can also be represented next to one access point, and that access point can be responsible for the processing and coordination of the nearby access points. Now we look at the time division duplex modeling, because that's also the one we are using. We are taking from the cellular massive MIMO, canonical cellular massive MIMO, and just channel modeling we are taking into account. And according to the block fading model and this time division duplex operation, first let's start with the block fading model, and during some coherent, during one coherence block, during some certain time and frequency block, we can assume that the channel behaves like a time invariant channel. So always in the baseband, it's a complex constant. So once we estimate it with the tools we use, then we can benefit from this knowledge, and we can design the pre-coding combining according to this channel. Because during one coherence block, multiple, according to the length of coherence block, symbols covered channel use appear. So we can use the same channel during one coherence block. And we can also, in line with the time division duplex, assign some of the channel users in each coherence block for uplink pilots to estimate the channels, and uplink data transmission and downlink data transmission based on the channel estimates. That's the logic. And there's an important assumption here for the self-healing massive MIMO. We assume entire network synchronized in time, and we look at the correlated Rayleigh fading channel modeling, and the channel between user K and access point L. Now there are two important indices here, the user equipment index K and access point index L. And when we look at that, this R is the correlation matrix. Normally it is critical, important in cellular massive MIMO when there are large number of antennas, but here in self-healing massive MIMO, we aim fairly small number of antennas. Nevertheless, it is still important to take into account the special correlation between the different antennas at each access point. And then we can also write average large scale channel gain, and it is constant throughout the communication. Like we can think of that, it is like macroscopic, describes the macroscopic fading. So it is, we can take directly this trace of special correlation matrix and takes the average of diagonal entries, summation of diagonal entries, and divide by number of antennas. And we are using, like, of course, some other models are possible, but distance dependent pet loss modeling, increasing with the pet loss, and also there's a shadow fading coefficient. And this special correlation matrix, there are several methods to model that, but we are using local scattering model. And we assume these N antennas are deployed as uniform linear array. So this sine term and cosine term coming from that. And this F is the special scattering function. So we can put anything we want to this integral. And there are some methods to compute this integral in closed form with good accuracy. So that's the main outline of time division duplex and channel modeling. Now let's look at the dynamic cooperation clustering for a scalable system. We told that, okay, we are aiming a finite number of users for each access point, but how to determine these sets? Because users also affecting each other in terms of interference. And there is an important thing, because it's an important parameter in also cellular massive MIMO, it's the pilot contamination. Because the number of pilots are due to in each coherence block, we can only allocate some part of the channel users to pilot transmission for channel estimation. So this is shown by tau p. So also it puts a limit to the number of orthogonal sequences, pilot sequences. If the pilot sequences are orthogonal, we can disseparate the channels perfectly in the noise-free case. But we are also aiming a large network. The number of users is much larger than the simultaneously served number of users is much larger than this tau p. Then some users are inevitably share the same pilot sequence. In that case, pilot contamination occurs. But then how to determine? Because now the important thing is that proposed in this paper by Emil Björnsen and Luca Sanguinetti, this algorithm is important because it just makes a design to reduce the effect of this pilot contamination in a simple and algorithmic way. And the idea is that each access point serves at most tau p users, one per pilot. So in that way, we are aiming not to like avoid the effect of pilot contamination to some extent. Not the same serving user by an access point share the same pilot. And also this computes local channel estimates for only those users, serving users, and the computes the other combining vectors in uplink, pre-encoding vectors in downlink based on these estimates. So in that respect, we are aiming both reducing pilot contamination and also aiming a scalable system based on the user needs. And we will use this, I will, because shortly touch upon on the uplink and downlink model. So this you will encounter this dynamic cooperation cluster matrices, but now you can think of as fixed matrices. Once determined as a like snapshot scenario, we know which access point serving which user. And if user K is served by user L, then this matrix is just identity matrix with the same size as the number of antennas per access point. And this set is denoted by calligraphic MK. So the access point indices serving user K. Otherwise, it is just 0. This is for notational convenience. And we are now continue with the first part in each coherence block, channel estimation with uplink pilot transmission. Now there are tau p orthogonal pilot sequences, but some users share the same pilot. And in that case, we use this PK set. PK set is the user indices that share the same pilot as user K. Now we will see the effect of pilot contamination, because normally received pilot signal at access point L is the summation of channels, all user channels and the pilot sequences. And there is a noise component, and this is the power, pilot power for user I, summation of all user components, and includes the outer multiplication of the channels and pilot sequences. And normally, if we are all using separate individual orthogonal pilots, due to this pilot disciplining operation here, we will obtain just the desired part. But now, since there is a sharing mechanism, there is an other interference here during the channel estimation, and it creates the pilot contamination. It just combined with the desired channel. And although maybe the user channels are independent, there is a now inherent correlation between the channel estimates, and this creates coherence interference, as we will see later. And now here, since we use Gaussian model for the specially correlated Rayleigh fading, we can like utilize minimum mean squared error in the linear form, because LMMSE is now the MMSE, and also benefit from the special correlation matrices of local access points, each access point. To some extent, of course, we can dissipate the channels, but pilot contamination is important. That's the reason from the very beginning in the joint pilot assignment algorithm, we take care of this situation. How we do that? This is the algorithm I mentioned, joint pilot assignment and dynamic cooperation clustering. And also it is a structure that it can be applied in a dynamic scenario, not like a snapshot-like scenario. Assume that a user comes to the network, a pair in the network, then it just points to the master access point, the best channel. This beta KL is the macroscopic large-scale fading channel gain. And among all access points, the best one is selected. And it is the calligraphic L, as you see. This is the master access point. Then this pilot assignment appears, and now you see K-1. It has a dynamic structure, because until that point, with the existing users, because K is the current user now, we look at the summation of the channel gains for each pilot that use the pilot T. We are just for each pilot, we look at the effect of this interference in the feature step. And we select the minimum of them. And we assign this pilot to the user to avoid interference. Then we also, the master access point also invites other access points. And in our algorithm, in the basic implementation of this type algorithm, the user cluster is formed by looking at each pilot. For each access point selects the best user. For each pilot, not more than one user is served by each access point. And we construct in that way these cooperation clusters. And this L is added for this L. That's the logic behind it. And we also look at the uplink data communications now. Now the channels are estimated, and also, of course, before the channels are estimated, we know we construct the dynamic cooperation clusters, because only the responsible access points estimate the channels. For both uplink data communications and downlink data communications, there is an important two operations: centralized mode operation and also distributed. In the centralized, these access points act as relays, just radio units, remote radio heads relays, and it takes the receive signal, after some initial RF processing, sends the receive signals to the CPU, and this channel estimation, receive combining for the soft data estimation, and data detection is done, implemented in the central processing unit. So that's the reason we model it like a concatenated channel. We concatenate all the receive signal for all the access points. But we are using here dynamic cooperation cluster matrices because these are important for a scalable design. And there is a receive combining vector. Here you see them separately for each user, but overall, this VK represents the overall receive combining vector using the channel estimates. But of course, it only affects the signals coming from the serving access point for user K. That's the reason there is a dynamic cooperation cluster matrix here. And in that way, using the tools from Massive MIMO, we can write the achievable spectral efficiency, because we are using the worst case additive Gaussian noise assumption here and compute this ergodic rate. And this is the effective signal to interference noise ratio. So we can do the decoding data detection part as we do in the additive white Gaussian noise case here. And now you can see the effect of channel estimates, of course, because channel estimates are utilized and their inner product between the receive combining vector is important. But the important thing is that these receive combiners are designed based on the overall channel estimates, of course, for the serving access points. Now, the optimum receive combining vector can easily be computed in the uplink case. So we have a form, but this form is not scalable because the complexity grows with the total number of users. So you see, although there are several serving access points, several subsets, we still add the all K users. So this is not scalable. But one heuristic approach is the partial MMSE combiner. And in that way, we only select the users in this set. And we can show that the cardinality of this set does not grow with the number of users. So according to our initial claim, we have a scalable system now in terms of signal processing and frontal complexity. And we only take into account the users that are served at this one common access point. That's the idea. And then the question is, what happens to the performance if we only take into account some limited number of users interference? But we see that, okay, now you see the cumulative distribution function of the spectral efficiency in bit per second per hertz. When you multiply the spectral efficiency with the bandwidth, you obtain the data rate, achievable data rate, and there are 100 access points in the region and 4 antennas at each access point. And this MMSE all is the optimum solution. Unscalable, but optimum solution. But we are only very actually close to this one when we consider partial MMSE combiner with the scalable dynamic cooperation cluster. So it is important we design a scalable system, but the loss is not so critical. This very leftward figure corresponds to maximum ratio combining, but since it doesn't take into account the interference suppression capabilities, there is a real performance degradation in terms of spectral efficiency. And the other mode of operation is the distributed uplink data communications. In this mode, there are two stages of data detection. First, access points perform some initial pre-processing for the only estimates, the local channel estimates, and apply some local receive combining. That's the reason we are just not writing the concatenated version, but apply some local channel estimate based local combiners, VKL version. Here we apply it to the serving user, served user, but there is also data detection part at the central processing unit. And instead of just blindly combining all these soft estimates, we just assign some weights, and these weights are designed in the long-term manner based on the large-scale statistics of the system. So they are fixed throughout the communications, we can say that. And in that case, we can also benefit from the massive, of course, this is a different type of operation, but the bounding techniques in the massive MIMO and achievable spectral efficiency can be written. In terms of these large-scale decoding vectors, large-scale fading decoding vectors, it is called, how to combine these soft estimates at the central processing unit, but also in terms of these instantaneous based on the local channel processing, local channel estimate processing. So still in the uplink, the optimums, there are some optimum receive combiner structures in the uplink because it is easy. And we have the optimum large-scale fading decoding based on the statistics of these channels and based on the correlation between them. But again, we see that this is not scalable. The reason is here clear because now we are adding all the users in the network, all the user contributions. But again, we can use the same trick and we can design a near optimum large scale fading decoding using the same set, this calligraphic SK, only taking into account the users that are served by at least one access point, common access point. That's scalable, but also we can design a scalable local combiner. This local combiner is based on the channel estimates. So it is designed like not once, but in each coherence block, it is like computed. But we can only select the user that are served by the access point L. This DL is the set of these users. So it is automatically scalable combiner, local receive combining scheme. And now you can see the performance compared to the optimum large scale fading decoding and also not partial, local partial, but local MMSC using all the users interference. This is the all access points serving all users. It is the best one, but we see very small drop with our scalable one, near optimum large scale fading decoding and local partial MMSC, dynamic cooperation clusters. And again, this maximum ratio combining does not perform very well. That's the thing. But I think I'm maybe, okay, couldn't arrange the time properly. So let's continue. Let's skip these parts and continue with the downlink data communications. In this downlink data communications, we have similar formulas, but now the thing is that the achievable spectral efficiency is affected by different users. So it is not easy to find the optimum pre-coding techniques, but in the centralized operation, this data encoding and transmit pre-coding is done at the CPU, and in the distributed operation, only data encoding is done at the CPU, and the access points locally apply transmit pre-coding based on the channel estimates. That's the idea. So the system models in downlink are exactly equivalent because there is nothing, a second layer of large-scale fading pre-coding is power control, power allocation take the role of this processing, just the design of the pre-coding. Whether it is designed centrally, this WI, whether designed centrally or distributed, that's the problem locally. And it changes spectral efficiency and design of transmit pre-coding. And again, the optimum solution this time is not like easy to find. Maybe some optimization problems can be written, but it is very like it's not like a scalable operation. So we can benefit from uplink downlink duality in designing some heuristic pre-coding techniques. And according to this duality theorem, one good heuristic solution is just directly taking the structure of the receive combining vector. So we can benefit from this actually uplink receive combining in the downlink operation. That's the idea in downlink. So when you look at some graphs, you will see the same names, the MMSE. This MMSE coming from uplink, not optimum one in the downlink. So here there is an interesting thing. MMSE all is not optimum because there is no guarantee for that. And interestingly, like dynamic cooperation cluster with some partial MMSE characteristics brings another layer of power allocation, power control here. So that's the reason we obtain larger spectral efficiencies here, because it's not good that all access points like shout at all, serve all users. It's like scream away all users. So here the optimum thing is it's not guaranteed with MMSE, and we outperform this scheme with a scalable one. We outperform the unscalable one. That's the interesting part. And now we will look at the end-to-end resource allocation aspects, but I will maybe quickly go through this part. First of all, I should mention that this inherent implementation, innate implementation of self-MMSE MIMO just very in synergy with the Cloud RAN, Cloud Radio Access Network structure, because there is a processing unit, there are some remote radio heads, and user equipments. This three-layer structure resembles actually the Cloud RAN. So it's the most promising architecture for the future self-MMSE MIMO systems when we look at them. So in our current work, in our current paper, we look at the problem not in terms of physical layer, but also from the perspective of end-to-end power consumption. How to jointly orchestrate the radio, frontal, and cloud resources. Now you see that this again clusters, shaded regions, these access points, but there is like another story. Optical network units, we benefited from the time wavelength division multiplexing passive optical network frontal technology. For a small scale system, we look at the performance. Now there are some digital units in the cloud part and optical line terminal. So how to assign these optical sources and digital unit resources are important here. But the main idea is that to benefit from the like power saving, to try to minimize the active digital units and active access points, because there is an idle power behind that. So it is important to design the system such that as sparse as possible to satisfy the spectral efficiency requirements, but also not to activate all the more than enough digital units or optical network units. That's the question. Now I will skip some mathematical details, but we are benefiting from the mixed integer secondary order con programming. And now, due to some binary variables to model this on and off modeling, we are just solving using this complex tool. And our aim is to allocate the transmit powers, also to determine these dynamic cooperation clusters, which access point will serve which user, and optical frontal resources, which line card should be activated, which digital unit should be activated, and what are the active access points, and what are the, of course, user and access point association. Now we are not using our original dynamic cooperation clustering algorithm, but instead design them using mixed binary second order com programming. So optimum solution is guaranteed, although it's a complex algorithm. We know to get some insights to look at a small setup with 16 access points, 8 users, and compare the self-MMSE MIMO with the small cell system. And the small cell system only selects the one access point per user, like a cellular structure. It models a cellular structure, but again, we are solving the same problem, just restricts the visible set, visible domain. In that case, of course, the objective function is better with the self-MMSE MIMO, but to be honest, I would not expect such a power saving. For example, for a spectral efficiency requirement of 1.25 bit per second per hertz for all 8 users in the area, this 14% power saving is possible. And also self-MMSE MIMO can provide greater spectral efficiencies. After some point, you are not seeing the small cell system values. The reason is that the problem is invisible. So there are two main benefits here. So it is important to look at the end-to-end power consumption, there are some energy saving opportunities here. We want to look at that due to less number of active access points and also with the digital units, frontal resources in the self-read network. And it also comes to conclusions, we can say that physical layer foundations are well established, and you can check our book for the details and detailed references. But how to deploy self-read massive MIMO functionality in a practical feature system is an open problem. And there are no important open research topics here, not in terms of physical layer, but also when we look at the system from the end-to-end network perspective. First of all, promising network architectures under the umbrella of CRAN and also in line with the current wave of Open RAN. What are the promising network architectures? Either to use double layer structures, benefiting from edge clouds, and how to allocate the resources between them, and benefiting from low-cost frontal technologies, because now we looked at a very small scale system, but how to benefit from, for example, millimeter wave, terahertz wave, wireless frontal technologies, and also handle the coming hardware impairments with it, not only because of the low-cost access points, but also with the low-cost frontal technologies, cloud technologies, and the energy saving mechanism in a dynamically varying traffic, because now we are looking at a snapshot like a scenario. But the question is that we cannot change the allocated frontal resources, digital units in seconds level. So digital unit is open, allocated for some processing. It should open for a certain period of time. So we should look at the problem from the long-term perspective. And also one topic that is not touched upon very well, like time and frequency synchronization, especially in this now Cloud RAN architecture. And these are some open research topics. And thank you very much for your kind attention. And if you want to check our book, these are the details. And again, thank you.